In this video, we're going to talk about the geometry of the surface area formulas. So we're going to see the geometric intuition behind both those two surface area formulas that we saw in our previous two videos. So let's start off in 3D. We've got some surface. Let's say here's our surface. And let's represent this with a position vector. We'll call that R. And let's say the position looks like X, Y, Z. So by doing this, we'll be able to derive both the surface area formulas at the same time. So whether our surface is actually Z as a function of X, Y, or whether it's a parametric surface where we tend to talk about the position vector, by just plugging X, Y, Z in here, we'll be able to think of it in both ways and basically get both formulas at the same time. We really want to focus on the geometry of where these formulas come from. So let's take a slice through our surface with Y constant. So I'll try to redraw the surface like we had before. Let's just pick a Y value, like say this one. And so let's imagine the plane on which Y is constant, and we're just going to slice through our surface with that plane. So what that's going to produce is a curve. So we can zoom in on this curve. And if we were to draw the tangent vector at any point on this curve, that's actually giving us R sub X. So we could say this is the tangent vector in the X direction. Notationally, we would call that R sub X because we took our position vector R, which we had at the top of the screen, and just took the partial derivative with respect to X. So by holding Y constant, we're basically saying we want to let X change, but keep Y constant. So that's telling us about our rate of change in the X direction. So specifically what that's going to look like, if you took your vector X, Y, Z and took partials with respect to X, you'd have 1 in the X direction, 0 in the Y direction because we're holding Y constant, and then in the Z direction, Z sub X. So you could do a similar kind of process by slicing through your surface and holding X constant. And what you would get then is a sense of the rate of change in the Y direction. So you could say the tangent vector in the Y direction, you could call that R sub Y. That would look like 0, 1, Z sub Y. So now let's go back to our surface and see how these tangent vectors are going to be helpful to us in computing surface area. So we've got our surface here. And essentially what we're doing when we're thinking about surface areas, we're thinking about little chunks of the XY plane at a time. So let's say this little filled in area here is dA. And what that represents is taking a small change in X, small change in Y. So you get this little rectangle in the XY plane. And we want to figure out how much area of the surface does that correspond to. So if we were to trace up this rectangle, trace it up to our surface. Well, because our surface is curvy, when we trace it up onto our surface, it's no longer going to be a nice rectangle. Most likely, it's going to be some kind of, let's say, parallelogram here, depending on how our surface is curving. So the area is going to be bigger and the shape is going to be, or the area is going to be different, bigger, most likely, and the shape is going to be distorted. So let's call this ds, meaning a little chunk of the surface area. Okay, so let's zoom in on this ds. So it's a parallelogram. I'm going to draw it like this. And let's see if we can figure out what the side lengths of this parallelogram should be. So if we think in the X direction first, let's think about what that side length should be. Well, our tangent vector in the X direction is going to help us with this, because the tangent vector represents the positional change that's happening in space if we were to take a full step in the X direction, so a step of 1 unit in the X direction. But we're not taking a step of 1 unit. We're actually taking a step of just dx units, so a tiny, tiny little step in the X direction. So that means what we should do to figure out this vector here is we should take our R sub X and we should just scale it. We should just multiply it by dx to say, oh, we're not moving 1 unit in the X direction, we're just moving dx units. So we need to scale that. And then similarly, if we want to think about what's happening in this direction here, there's change happening in both the Y and the Z directions. So the surface is not typically flat. It's not usually parallel to the XY plane. So we could actually draw that parallelogram even a little bit more distorted to emphasize that. Okay, so I feel a little bit better about this parallelogram here because it no longer looks like it's right parallel to the y-axis. So you got change here happening in the y and z direction. And if we ask how long is this side length here of this little parallelogram, well, it has something to do with the tangent vector in the y direction, but it's not quite r sub y because that would correspond to taking a full step 1 unit long in the y direction, and we're not doing that. We're just taking a step of dy in the y direction, so we need to scale that by dy. All right, so this zoomed in parallelogram here, the area of this thing is ds. So let's say ds, our little chunk of surface area, is the area of this parallelogram. And then we're going to have a little flashback to linear algebra to remember how to calculate the area of a parallelogram. So if you know the two vectors that are forming the sides of your parallelogram, you can say your area is going to be the length of the cross product of those two vectors. So we are going to take the cross product of r sub x dx times r sub y dy. That's going to give us a vector in 3D, and then we'll just calculate the length of that to find the area of our parallelogram. Now dx and dy here are constants. They're just representing the side lengths of this little tiny rectangle in the xy plane. And so when you have constants multiplied on with your cross product, you can just bring those constants outside. So we can put the dx dy at the back, no problem. It's really these vectors r sub x cross r sub y that we need inside there. So we're going to cross these two tangent vectors together, calculate the length of that cross product, and then scale by dx dy. Okay, now if you wanted to move away from notation and you preferred to make this more computational, you could look back at our formulas for r sub x and r sub y, and you could think about actually computing that cross product. So on the side here, I'll think about it that way. So r sub x was 1, 0, z sub x, and r sub y was 0, 1, z sub y. And if we want to do the cross product, I'm just going to do the cross product the fast way, where I copy out the first vector, recopy the first couple columns, etc. And then we're just going to calculate a couple of 2x2 determinants. So if you wanted to make this explicit, you could say, okay, then we're talking about the length of the following vector. So computing the cross product, you'd have minus z sub x minus z sub y and 1. We still have our dx dy at the back. And the length of that vector is just going to be square root of your components squared and summed up. So we usually write the 1 at the front just because it looks better. So 1 plus the square of z sub x plus the square of z sub y. That's all under the root, and then we'd have our times dx dy. Okay, so two of these quantities should be looking pretty familiar, this one and that one. These are basically giving us the integrand that we need to compute surface area, because we're saying these quantities are d of our surface area. So to get surface area, if we just call surface area S, you would say S is double integral of ds, just like, let's say A is the double integral of dA, for example. So just notationally, that's what our ds is representing. Now for surface area, I just tend to write it as SA. So this ends up looking like SA equals double integral of ds. But by looking back over our calculation here of ds, we now see our two formulas popping out. So we've really got two situations. One is the situation where you've got z is a function of xy, and the other situation is where you have a parametric surface. Okay, so let's write down the formulas in those two situations. So if z is equal to f of xy, we use the bottom version of ds here. And we say just integrate over the appropriate region, the square root of 1 plus z sub x squared plus z sub y squared. And then at the back, you could just write dA, or you could write dx dy. So that's the most common situation for surface area, where you've just got z given explicitly. But if someone did give you a parametric surface, like for example, the cone or the paraboloid that we saw over our previous 2 videos, then you would think about doing this process of taking the partial derivatives of your position vector, crossing those together, and then taking the length of that. So you'd have the double integral over the appropriate region, the appropriate range of your parameters, and then integrating that length there. Now, this comes out written in terms of x and y just because of the notation that I chose for the problem. But typically, if you're calling your parameters, say, u and v, then this would look like r sub u cross r sub v, take the length of that, and then that would force your differentials to look like du dv. And then r here just represents whatever u and v values were given in the problem. So that is the geometry behind the surface area formulas. If we just flash back to our picture to see the really important idea, geometrically, you're taking these little tiny chunks of the xy plane, tracing those up to your surface, and you're figuring out, okay, how does that area get distorted by the curvature of the surface? And if we zoom in on that little chunk of surface area, ds, it really has to do with our tangent vector, because that's what's telling us how much z is changing as we take little steps in the x or y direction. That's what's going to capture how distorted our area becomes. So thanks for watching the geometry behind the surface area formulas.